All right, so let's talk about another type of signal here, okay? Let me draw this one out. So let's say I'm just doing a steady increase here, right? And then something happens, and then maybe I go like this again. Okay, so in this situation, if I'm just doing exception reporting, this value changes, this value changes, this value changes, this value changes. I'm taking a bunch of readings here, but really this is a line, right? So what would really be nice is if I could take this reading here and this reading here and know that I just have to draw a straight line from it, okay? And so what I can do is just like, so what happens with exceptions is I define a deadband, okay? So I take a reading. Let me redo this. Okay, so let's talk about exceptions. Okay, so I take a reading here, and I draw a little deadband. So I say I don't want to record the readings unless they go outside that deadband. Okay, so they go outside the deadband right here. So I take that reading. Okay, so I'm going to redraw this, and then I draw my deadband around here again. And so I say if it stays within this deadband, if it doesn't deviate by a certain level, let's not take it. Okay, so that's exception reporting. Okay, and one of the nice things about that is that I can specify this deadband. And so this allows me to filter out noise. Maybe I have a signal and I'm getting noise in the signal, right? It's a bunch of little stuff like this. And then something happens, and and then there's a bunch of noise in here. Okay, well maybe this little deviation in here just isn't important to me. I know it's noise, it's not important. And so what I really want to store in my historian is a cleaned up signal that looks like that. Okay, so that's why I would define a deadband. Okay, and that's my exception, my deviation and my exception. So I say if it's inside this deadband, just filter it out. I don't need to see it. There's no reason for me to have all these little readings in my database taking up a bunch of space when it's just noise. Okay. Now the next case is where the problem with exception reporting is that it has to be a horizontal line like that. So when I have something that happens like this, it's still linear, but if I'm just doing exception reporting, these values are all changed. And so, even though it's not a very interesting signal, I'm using up a bunch of my space again. I'm using up a bunch of storage space, and then that's going to affect my performance when I go to look at the historical data. And so really what I want is an algorithm that will take less data on any kind of a linear signal, right? And then take more data when it's not really all that linear. Okay, and so there's this algorithm called the swinging door algorithm. And so what I do is I take 2 points and I establish a slope, okay? And then I've got a deadband outside of that. And I say as long as my point's coming along here or inside that deadband, I'm going to ignore them. But as soon as one of them goes outside my deadband, so let's say this one goes outside the deadband here. Let's say I take a point here. What I'm going to do is I'm going to draw my line to my last reading before that one, and then I'm going to go and do a new slope, and I'm going to take readings along there, and I'm going to ignore them until they go outside, and then I'm going to take my next reading. Okay, so this is called the swinging door algorithm, and what it is it's just a way of taking my signals, my signal as it comes in, and during times when it's relatively linear and uninteresting, I'm not taking a whole lot of readings. But again, when something like this happens, I'm going to be taking a bunch of readings here because the slope of the line's changing all over the place. Okay, so this is kind of cool because what's going to happen is when I read my stuff back from the database, I'm going to end up reading back points, say something like this. Okay, and then I'm going to reconstruct my signal line, and it's going to go like that. Okay, so this would be compression using that swinging boxcar algorithm. And so during times when the data is not very dynamic, I'm not using a lot of space, to store the information, and then during periods of time when it is very dynamic, I'm using my database storage to capture that dynamicism. So this is kind of an optimized way of saving time series data, and this is what, at least the historian that we're going to be showing you, this is the method that it uses to save the data. It's very important that you understand this, and there's going to be some associated reading material and everything that'll cover it as well, and some other examples of it. But basically, swinging door or swinging boxcar algorithm is what this is called. Okay. All right. So just to go back through this this whole data flow from the very beginning. Out in the field, we have our instrument. Okay. And that's going to be plugged into a PLC and an RTU somewhere, and either through a 4 to 20 milliamp signal, or maybe through a serial line talking Modbus, or some other protocol, we're going to talk to this instrument, or we're going to collect data from this instrument into the PLC, where it's placed into a tag. Okay. This PLC is networked into a SCADA system, some sort of a SCADA master that pulls it. Okay, networking is going to be TCP/IP pretty much always, and it's probably going to be some flavor of Ethernet that's being talked here. Goes into the SCADA system in the control room. They use this, they build their little displays, and they have their trends, and they have alarm screens, right? And status displays and all of that. And so they operate the electric grid, and maybe through this same thing there's a switch here that they can open and close, or some sort of action that they can take, some sort of outputs that are happening as well. And so the SCADA system controls. And then coming out of the SCADA system, a system integrator through some sort of a firewall can send data to the third-party systems where people can use them. Okay. So, third-party system here. What I'm proposing is a data historian. It takes the readings that have been collected all the way up through here into a time series, right, of a tag, a time, a value, stores it all in my historian so that people can get to it. Alright, so that's starting at the very beginning where we started several lectures ago, on up to the big picture of what's happening. I get my time series data in my data historian. So, and the reason we like this data historian and we like to have this data store is that it's very nice to be able to go back and say trend these instrument readings, you know, maybe for a full year, and see seasonality and trends, and be able to analyze this data and figure out how much power we're producing and how much customers are consuming and when they consume it, and just all that kind of stuff. So this is why we want a data historian. This is why we want the third-party data historian. It provides secure access to the data outside of the control system, which you know, the primary responsibility of this control system is to operate and maintain the electric grid safely. But we've now talked about the historian and some of the characteristics of the time series data and how we want to store it. That, you know, during times when there's not a whole lot happening, we don't want to spend a whole lot of database space tracking that, and when something really interesting happens, we want to capture that dynamicism and be able to see it in our trends, right? So this is where we're sitting right here now. We're going to start talking. The rest of this course is going to be talking about this historian and using this historian and the tools of the historian, storing our time series data. And that, so but at this point you should pretty much understand how the data is collected, how we instrument the grid, how the data is collected, how it's networked, how it communicates it up to the control system, and how it makes it to this third-party historian.